One of the main design drivers when deploying wireless sensor networks is the spatial coverage of the measurement area. We often set up a network in a way that each sensor covers as much area as possible. But whoever worked with low-cost sensors knows that especially these low-cost sensors can give unreliable measurements or can even fail completely. Therefore, we argue that redundancy in the network should be an additional design driver during the deployment of this wireless sensor network. For a wireless sensor network that we deployed in a steel factory, we analyzed the correlations between sensors and built machine learning forecasting models to investigate how well the whole network can compensate for the outages of sensors. This is a simplified layout of our sensor network. We deployed 16 stationary sensing nodes equipped with sensors for dust, gas, temperature and relative humidity in a measurement area that is about 150 times 30 meters large. Within the measurement area, metal slabs are moving on a roller table and are rolled by multiple mills. These mills roll the metal slabs to centimeter thickness to a few millimeters and coil them up eventually. So there's a lot of dust emerging during this process, and therefore dust is the main target or agent of interest in our following study. When we look at the correlations, so here are the correlations for dust, temperature, humidity and gas, we see that generally nearby sensors are more correlated than sensors that are spaced further apart. But we also see that there are some sensors in special positions, for example this one here or this sensor here, that share a very low correlation to all other sensors. So this indicates that the sensor network should probably be more dense around this area. However, when we look at the rolling correlation, so here we have a rolling correlation over a window length of 1 day, we see that even highly correlated sensors like these three here fluctuate substantially over time. And this indicates that there are spatially very limited events in this area that would result in non-detection if we sparse out the sensor network in this area here. We then built multiple machine learning models. Here you see the time series for one sensing node. This is the data that we used for training of the models. And then you see linear regression and profits forecasting model compared against the test set. We then performed a backward elimination to evaluate how the forecastings depend on remaining sensing nodes. That means we trained for each sensing node 9 different models and then successively removed the amount of remaining sensors in the network that were used for forecasting the sensing node. If you are interested in more details on this, I invite you for discussion in the live session, and thank you for your attention.